Recording in progress.
Okay, hello everyone. Thank you all for being here and welcome to a new Cosmos seminar. Today I'm very happy to introduce you to Macarena Lagos from Columbia University. A little background about Macarena. She obtained her undergrad and master's degree at the Pontifical Catholic University of Chile. She then received her PhD at the Imperial College London. And she also held a postdoc position at the University of Chicago. And now she's a postdoc at Columbia University. Macarena's research is mainly focused on understanding the origin and evolution of the universe and its constituents, as well as the behavior of gravity in the extreme low and high energy regimes. In particular, she works on topics such as dark matter and dark energy, the initial condition of the universe, and the physics of black holes. Today, her seminar is titled Lensing of Gravitational Waves. So thank you very much, Macarena, for accepting our invitation, and please take it away when you're ready.
Thank you. Yeah, thank you everyone for making the time to be here. And since this is a cosmology seminar, I may go a little bit fast in some parts, but feel free to stop me at any point if you have any questions. So, well, I'm going to talk about lensing of gravitational waves. So I'm going to start by telling you a little bit of gravitational waves first. So gravitational waves are these oscillations of the space-time. And currently, they are detected only when they come from a merger of two compact objects that have very strong gravity among them. And typically, these are black holes or neutron stars so far. So what you see here in this picture is the typical scenario that we have in mind. So there's two compact objects merging, and they are astrophysically far from us. And first, in order to understand the signal that we detect, we need to understand the formation process that depends on the strong gravity physics. It depends on the behavior and the physics of these objects, their masses, spins, compositions, whether black holes are described by the theory of general relativity, or maybe there's something different. And it contains information about the dynamics of these objects as well, like the properties of the orbit. But after the signal has been emitted, and it propagates for billions of years towards us, and that is when we learn about cosmology. So this propagation of gravitational waves are sensitive to the expansion history of the universe, like H0, the expansion rate, to the properties of dark energy, and the properties of dark matter as well. And that's what I'm going to be focusing on mostly, the effect of lensing, when these waves encounter some inhomogeneity along the way, and they have this effect. So this is what a typical signal looks like. You may have seen this before. So what we detect is called the strain, which is a particular combination of how the signal is interpreted in the detector as a function of time as the two compact objects are evolving and getting closer and closer to each other. So these binary systems are special because the signal that they emit has a coherent phase, a coherent polarization, so we can extract all of that information, the amplitude as a function of time, as well as the phase and possible polarization. So that is in principle the general idea of like the type of signals that we're going to be detecting. And in the 2020s, or even, well, starting in 2015, with the first detection of gravitational waves by the LIGO Virgo detectors. And currently they have claimed to have detected 90 of these mergers, mostly coming from black holes. And in a few months, at the end of May, they will start running again. So they have not been detecting anything. They've been on pause since the beginning of the pandemic. But at the end of May, they will run again together with Kagra, which is a new detector in Japan. And they may be detecting an additional 100 of these events in a single year. And in about 4 years, they will increase sensitivity and be detecting about 1,000 of these events in a single year. So this is like the future plan for the 2020s, but we already have plans for the 2030s. So there are detectors planned here on Earth as well as in space. So on Earth, hopefully we're going to have Cosmic Explorer in the US, an Einstein telescope in Europe, as well as LISA in space. So in the 2030s, of course, these detectors are going to be much more sensitive, and we're going to be having 1 million of these events per year. So certainly there's going to be a lot of information, And what I want to emphasize is that even though we think of black holes mostly and strong gravity physics, they will carry important information about cosmology. So this plot is showing how far I can detect a binary merger in redshift, depending on what is the possible mass of this merger. So we don't know exactly what should be the mass of these black holes. So these lines are usually called the horizons. So the blue, let's look at the blue. So these are the current detectors when they're working at their design sensitivity for years. And they can usually see as far as redshift 2, maybe at that time. Currently, all of these 90 detections have a much lower redshift. Most of them have redshift 0.2 or 0.3. And I think all of them are below redshift 1, but this is in 4 years. And then what I want to emphasize is here in the 2030s, right? So let's look here at the green and kind of pink curves. Yes, it's visible. Where you can see that if there are any mergers happening at redshift 100, then they could be detectable if they have this type of masses. So certainly gravitational waves travel rather freely through space, and we can reach very high redshifts that are many times inaccessible with electromagnetic light. So okay, let's learn some information about cosmology with these gravitational waves. And I already mentioned that we can learn about kind of the standard expansion history of the universe, but I want to focus on the presence of homogeneities. What happens when they encounter a galaxy or a cluster of galaxies? So this phenomenon is what we call gravitational lensing. We exploit a lot with electromagnetic signals. And so very broadly, gravitational lensing happens when any signal is propagating through this curved space, and its path is going to change. So for electromagnetic light, we know that it has been used to learn about dark matter, large scale structure, properties, distributions, to measure the expansion rate of the universe, to see faint objects, because usually gravitational lensing leads to magnifications of the signal, and to detect objects that don't even emit any light in an indirect way, such as small planets, exoplanets, or even primordial black holes. So this is like examples that you see here in the bottom pictures. So on the right here is a famous bullet cluster in which a reconstruction of the dark matter distribution around this cluster was used through the method of gravitational weak lensing to find out that dark matter is definitely not a strong gravity. It's not a modification of gravity. It's something separate because it has a different distribution than luminous matter. So certainly we are exploiting this a lot, and we want to do the same with gravitational waves whenever it's possible. And in particular, I want to talk about a strong lensing of gravitational waves. So normally we have two regimes in lensing, which is weak lensing and a strong lensing. But for weak lensing, because it is a weak type of effect, you need a lot of sources, and we're not at that point yet. But a strong lensing, you need just one single source that has to be very aligned with the lens, whatever the lens is. It could be a cluster or a galaxy, and the observer. And whenever that happens, even for a single event, then you're going to have this effect of a strong lensing. So in a strong lensing, what is the effect? When you have this high alignment, typically there's going to be multiple paths that the signal can take from the source to the observer. And that's going to translate into the creation of multiple images. Each one of these paths also will create an image with a different amount of magnification. So you have to imagine that the light is kind of focused or defocused around this path, depending on what is the curvature that they are feeling. They will arrive at different times, so there are time delays. And again, because of the different paths, they will seem to come from different positions in the sky effectively, even though they come from the same source. So this is an example of what this looks like for electromagnetic signals here. At the center, we have a typical situation of a source that is called a quasar, and it is being strongly lensed by a galaxy. So these 4 white dots that you see here are 4 images from a single quasar. And here at the center, you see the light from the galaxy that is creating the effect of the lensing. And this type of images and detections, for example, has been used to constrain H0, the expansion rate of the universe, because the time delays, the arrival times between the images depends on the travel path of the images, on how long they've been traveling for, and therefore the expansion of the universe. And so far, 7 of these type of quasars, strong lens quasars, have been used to set an 8% precision constraint on H0. It's not the most competitive constraint that we have right now, but it is a way of getting there at some point with more specifics.
I was still like more like a naive question. And why are there like 4 dots and not a continuum distribution of why 4 dots and specific paths for the gravitational lensing, and not like a continuous distribution of
Yes, so there are two reasons. One is that the source is a point source. So it's very localized, a point source. You had a galaxy, then normally you see arcs, for example, so that is more of like a continuous type of image. When the source is very compact, such as it's a point, then you see points as images. And also, that I'm gonna get there later, is that the places where these specific images form is because there is constructive interference among the paths. I'm gonna get there, but that's a general idea. So the other thing that I want to emphasize is that these strong lens images basically tell you about all of the properties, the magnifications, and the time delays depend on what is the matter distribution of the lens, whatever is causing the lens. And the lens doesn't need to be luminous. In this case, it was a galaxy. There is some light that we see here at the center, but it could have been a completely dark object. And the only thing that lens improves effectively is the gravitational potential. So it is like an excellent probe of dark matter. And the dark matter distribution in the galaxies is going to affect these time delays and magnifications. And this is actually the main reason why the precision on H0 on this constraint is only 8% and not better, because there's a lot of uncertainties on what is the dark matter distribution in the lens. So in principle, the physical phenomenon is exactly the same for any kind of signal. So lensing is a generic type of effect, regardless of what is the signal propagating. But there will be some kind of practical differences that we need to take into consideration when thinking of lensing of gravitational waves. So first of all, for example, in these quasar images, you see that the 4 images are typically separated by this distance, angular distance, which is about 1 arcsecond. So you need to have very good spatial resolution here, angular resolution in your telescope to be able to distinguish the images and their locations, which is a very useful information that we use. But for gravitational waves, because the way the detectors work, so it's not like a telescope that you point, it's just sitting there, and the gravitational wave can come from anywhere and it will be detected. But if you have many of these detectors, then you can make some triangulation and find out where the source is. But even with many detectors, what we believe we will have in the future in practice is about 1 degree angular resolution, which means that if we do have this type of situation in which we have a gravitational wave source that is being lit and 4 images are created, the 4 images will seem to come from the same place in the sky. We will not be able to resolve their different locations. So that is information kind of lost that we will not have in these type of detections. But we do gain in other kind of observables, which has to do with how we measure the time delays. That is, I already said that the time delays is a very important information, for example, to constrain H0 with this type of systems. And for quasars, the precision in which we measure the time delays is of about 1 day. But for gravitational waves, currently, we detect gravitational waves that have frequencies of 100 hertz or 1,000 hertz. And that means that we can resolve time differences of milliseconds. So that is how well we will be able to point, the arrival time of each one of the images. So there's some interplay here on information gain and loss, and in the future, the hope is to combine, of course, all of the information from electromagnetic signal and gravitational waves to have the most. But so since we do not resolve the sky location, then I already said, if we have a binary black hole merging, then we will just effectively detect different images. I want to call them images. So different gravitational wave events that arrive at different times, but they seem to come from the same place in the sky. So this is a toy situation, a kind of a figure of a signal, a binary black hole merging that is strongly lensed, and the observer receives two images. So that means that you receive one gravitational wave signal, and then sometime later you receive another one. They have different amplitudes because of this effect of magnification or demagnification that is common in strong lensing. But aside from that, everything seems to be the same, like the sky location and the morphology, like the phase evolution that we see here. So that translates into these two events that in principle, we don't know if they are related. They should have the same kind of, when we compare to general relativity, we should estimate that they have the same spins, the same masses, and everything should be the same, aside from the amplitude. So it seems that we do not have a lot of information because we can have 100 or 1,000 detections, and we just have to search for pairs that have similar morphology, and they just arrive at different times and different amplitudes. And have the same sky location, but the sky location, as I said, is not super precise. So, for example, if you look at the first 10 gravitational wave detections that happen, so this is what this picture is showing. These are the simulations of the first 10 detections. We the masses that we thought we think they had, and because of different biases and the procedure in which the detections are made, it turns out that a lot of these signals have a similar morphology. They have a typical similar frequency range because of the detection limitations. So having a pair of signals that have similar morphology, but different amplitude and arrival time actually can happen just by chance. And from these first 10 detections, for example, if you go through like an actual numerical analysis of the data, you can find that these two events come from the same place in the sky, given the large uncertainties of that. And we call them lensing candidates. So they do satisfy all of these common properties that they could be lensed. So how do we know if we have actually already detected the first strongly lensed gravitational wave event? Well, we don't know. We need more information. Yes. And there are two questions.
How far apart are they?
In time.
Yes.
Yeah, so here you can see the dates. So this is January 2017, and this is August. So yes, that is a very important piece of information that we should use as an additional piece. So we know from electromagnetic observations that the typical time delay between images should be a month or a few months, a couple of months. So having these that is already like 7-8 months, it start becoming unlikely. And this is the additional information that we need to incorporate to be able to confidently say whether we have a pair that is strongly lensed, which we call the lensing priors. So we have some prior information on how many galaxies there are, the distribution, their masses, and therefore how likely it is to have a strongly lensed event already. And if you take everything, yes. Yes. Yes, so there's also, you can also calculate a typical magnification, right? If the magnification, so if the difference in magnification is like way too large, that becomes more unlikely. So this will be incorporated in the lensing priors. In this case, it doesn't seem to be super different, the magnifications between them, and somewhat different. So I wanted to tell you, just a final result. If you do incorporate all of your lensing priors, like what is the typical time delay or magnifications, and what is the typical rate at which you should expect to have a strong lens event according to the number of galaxies that we know, then for the current detectors, so for their sensitivity, the current rate is 10 to the minus 3 to 10 to the minus 4. So this means that only 1 in every 1,000 or 10,000 events should actually be strongly lensed. So having 1 in the first 10 detections is extremely unlikely. So I think in general, the community believes that we have not detected the first strongly lensed event. However, in the future, so when the detectors in 4 years are detecting 1,000, 2,000 events in a single year that I mentioned, this is the LIGO CAGRA, at design sensitivity, then we should expect to start seeing the first. So we want to prepare for when this is coming, that hopefully will be soon. In the 2030s, it will definitely happen. We could have 100 of these strong lens events in a single year for Einstein telescope and cosmic explorer. So these are the typical rates. So if we want to prepare for the first event that's going to happen in 4 years, and maybe there's going to be the first one, and we're going to have a catalog already of 1,000 events, then how do we separate out the one that is truly strongly lensed from all of these lensing candidates that are just coincident pairs, we call them? So most likely we will need some electromagnetic confirmation. So all of these mergers, we believe that it's likely they are happening inside a galaxy, right? So if there is a merger that is strongly lensed, then the galaxy that is hosting this merger should also be strongly lensed. So we should search for all the strongly lensed galaxies that could be the possible host and confirm whether they have compatible observables and both are strongly lensed. So that's, I think, the way we'll have to do it eventually. But there is still additional information that we can use, which has to do with the fact that I have not discussed that strong lensing can also affect the phase of the signal. So far I've been talking about time, arrival times, and magnifications, but not about the details of the morphology and the phase. So if lensing leaves any signature in the phase or the polarization, then we can use that information. And this is very particular to gravitational waves, because for electromagnetic signals, we normally don't measure this type of observables. We just have some kind of average intensity quantity that we measure. So there's no phase and polarization that is coherent that you can detect. So it turns out that strong lensing does affect the phase, and in particular, the different images that we will receive will be shifted in the phase by π.5. So I'm going to explain why, but first I want to give you an intuition of what this sentence means, having a π.5 phase shift. So here on the left, I'm showing the same plot that I showed you before. So this is a toy situation of binary black hole merging that is being lensed and 2 images are received. So this is the first one, and this is the second one. So then on the right panel, I'm gonna superpose them both in time. So I want to compare their phase evolution. So I put one on top of the other, and I also rescale the amplitude because I want to isolate only the phase difference. And this is what you get. So in green, is it? Yes. In green, you have the first image, and in this kind of purple line, you have the second image. And here on the dashed line, you can see that they have the same amplitude evolution as a function of time by this envelope that you see here, but the actual value of the phase at any given time is different by π.5. When one is in a peak or a trough, the other image is in a low. So this is what I mean by the images are shifted by π.5. So since we measure the phase, this is a signature that we will use. When we detect 2 images, they need to be shifted by π.5. If not, then most likely they're not lensed. And so why does this happen? And this is something that happens to all signals. The only reason why it's not relevant for electromagnetic line is because we don't measure phase. but it also happens. So, and this comes back to your question about why we have individual images. So in principle, when we are analyzing this scenario of lensing, we think of this type of situation. We have a source that is emitting in all directions, and we have a lens that effectively is very thin for these cosmological distances, so it is a three-dimensional plane. And then we have an observer. So from the source that is emitting in all directions, in principle, we should consider and follow up all of the possible paths that the signal could take that could travel from the source and end up arriving to the observer. But there are special locations of this path, or there are special paths, which is what I showed here on the right, which is there are special paths in which constructive interference happens, because if you start adding up all of the different paths and the signals that take, they're going to arrive with different phases. They took different paths, they have different arrival times. So they may arrive kind of all out of phase, cancel out, and you don't see anything. But there are special paths where constructive interference happens, and that is when an image is going to form it along that path, along that location. So what are these special paths? These are paths with what we call stationary time delays. What this means? What this means is that a path could be a minimum in time delay, meaning that all of the neighboring paths are going to take a little bit longer to arrive. So that is one example of a stationary time delay path. When that happens, then you have constructive interference. But you could also have other type of a stationary time delay paths, which are a maximum, for example. So all of the neighborings take a little bit shorter to arrive, or a saddle, because we have a bidimensional plane. So all of the images that we always detect have to be of either of these three types, because that's why the image has formed, because they are stationary time delay paths. So effectively, when we try to then take into consideration this interference effect, you have to actually iterate out over all of the paths to calculate the total signal that you detect. This is what you get. So I'm writing like the equation for the signal in frequency space, so in Fourier space instead of as a function of time. So the unlensed signal gets a first correction, which is an overall magnification, an overall rescaling. So this is the well-known effect for electromagnetic lensing. Then the second effect that you get, like here, because we're in Fourier space, appears just as a phase proportional to the frequency of the signal, is a time delay. So the curvature is going to create this time delay. So again, this is a well-known effect. But now, because of the interference of all of these paths, then you're going to have an extra phase shift here, that it is a frequency independent phase shift. So it's different to the time delay term that you see here, that is proportional to F. So it's a different physical effect. It's just a constant phase shift that the exact value that this phase shift takes depends on the type of stationary path that you had. So different type of net interference effect is going to happen. So for the minimum images, the phase shift is actually 0. So the signal is not phase shifted compared to the emitted signal. But saddles get a pi.5 phase shift, and the maximum get a pi phase shift. Okay, so what this means effectively in practice is whenever I receive a minimum type of image, then these type of images actually look the same as an unlensed image. Like as an individual gravitational wave event, I cannot really say whether it was a strongly lensed or not, because the only difference that happened between lensing and unlensing is a change in the magnification, which is degenerate with changing, for example, making the black holes more massive. You can increase the amplitude and the arrival time, that is just arbitrary. So these minimum type of images as individual events always look unlensed or could be confused with any unlensing. And similarly, it happens with the maximum. So having a pi shift is just an overall change in the signal, like a minus sign. And those, again, a change in the signal could be mocked by kind of rotating your binary with respect to your detector. So those always look unlensed. But the pi.5 ones actually can definitely not look unless. So you could, by detecting individually a subtle image that has a pi.5 phase shift, you could be able to say, this is not compatible with any of my unlensed models of signals, so it has to be lensed. And this is why it's very important to take into consideration this phase shift as a lensing signature. So let me, before showing you an example of how we see that it definitely does not look unlensed, let me go back again to the same toy situation that I showed you. So the first image, this is the second image. So whenever we have two images, typically the first one, I mean, always the first one is a type 1 by definition. It's the one that takes the shortest time to arrive. So like this one always has a 0 phase shift. And the second image, most of the time, is going to be a type 2 image. So the most typical strong lens situations that we're going to see is one type 1 and one type 2. And they're phase shifted by pi.5 among each other. And this is what I showed you before. So these are the two different type of images, and they have a relative pi.5 phase shift. So in this case, I didn't tell you before, but this type of binary gravitational wave signal comes from a binary merger of equal masses, which is most of the time what we think we have detected so far. But also, so this is the Q parameter that is here at the top. This is the mass ratio between the two black holes. And this iota tells you what is the orientation of the binary with respect to the line of sight. So, the two black holes are moving in a plane because they are, rotating around each other. And this binary plane has some kind of inclination with respect to or line of sight. So the signal looks the simplest in these type of situations when the two black holes have the same mass or nearly equal masses, and the binary plane is perpendicular to the line of sight. So this is what we call face on or face off. And in these cases, well, I already told you the type 1 images could be very well mimicked by any changes in the source parameters. So by detecting a type 1 image, we wouldn't be able to say, oh, this was definitely lensed. The type 2 image in these type of simplest gravitational wave signals could actually also be mimicked by a change of different angular parameters that give you exactly a pi.5 phase shift. But most of the realistic situations will not be inclined, will not have exactly equal masses, and in that case, we're going to see that this pi.5 phase shift is going to introduce a distortion that I'm going to show you next. So this is what I'm saying here. So more complicated binary systems get actually distorted. And something that I already tried to emphasize is that this phase shift is really just a constant change in the phase. It's not equivalent to a change in arrival time. It's a different physical type of effect. So this is a more complicated type of gravitational wave signal that has unequal masses. So the mass ratio is 0.1. So one black hole has 10 times the mass of the other one. And this angle here is the inclination of the binary plane with respect to the line of sight. So pi/3 could be a very typical value. Having Q equals 0.1 has already happened in some of the detections, but it's not the most typical value so far. So this is a situation to try to illustrate an extreme case. So this is the same kind of mock scenario where this type of binary with an equal mass and inclination is strongly lensed, and you get two images. The first image is always a type 1, the second one is a type 2. So we do the same exercise here on the right of putting them on top of each other to compare their phases. And you see that green is a type 1 image, and the kind of dark purple is a type 2 image. And now they don't look like they have the same morphology, only because of the pi.5 phase shift. So the signal has been distorted. And what you see here is cyan, but it's over there. So the cyan is like the best that we could try to reproduce the type 2 image with an unlensed waveform. So what if we thought that that second gravitational wave signal that arrived was unlensed? That's what we do most of the time. We assume that all of them are unlensed. So we try to fit these different binary parameters to that signal. And the best that we could reproduce is this cyan line, which, as you can see here, is definitely not the same as the purple one. And this is the statement that I've been saying, that these distortions definitely look not unlensed. So for unequal mass or inclined mergers, this is going to happen, that the type 2 images are distorted, and most of the case, we do expect to detect these type 2 images. So just by detecting the type 2 images of the distortions, we will be able to identify that there is a strongly lensed event in our catalog. At least for the future Einstein telescope and cosmic explorer cases, for example, we expect to have these detectable distortions of type 2 images in 10 or 15 strongly lensed events per year. So this is like a technique that's that can be used to detect strong lensing sometimes when we have this kind of complicated morphology for gravitational waves. So at least in those cases, we can use this phase information. So, so something to emphasize, whenever we detect a single event, let's say the first strong lensed event that's going to happen, we're going to receive a type 2 image, then maybe it's going to be distorted because maybe the binary merger was inclined. So then there may be some initial confusion as to whether there is some kind of evidence for modified gravity or modified cosmology as opposed to lensing. And this is an important risk to analyze because currently all of the detections are compared to either unlensed gravitational wave models or modified gravity, but they never, because it's thought to be unlikely to have a strong lens event, then they're never compared to actual lensed waveforms. So what we did and what I showed here in this plot is how well a modified gravity waveform can actually mimic that type 2 lensed image that is just in the frame of general relativity, but it's lensed and it has this 5.5 redshift. So there are a lot of different type of like modified gravity models that people consider in the literature. So many of them can be parameterized through a change in the dispersion relation. So basically it's equivalent to saying different frequencies of the wave are going to travel at different speeds, and that's going to create some distortion in the signal when it propagates from the source to the observer. So this is in this equation here, if you set A equals 0, then you get the basic dispersion relation of general relativity, and this is the basic naive form that we always assume. But if you add here some non-zero correction for A, then there will be a modified dispersion relation, and the signal that arrives will be distorted. But now, not because of lensing, because of this modified dispersion relation. And by changing here the power of alpha, so K is the wavelength, you can describe different type of models. For example, alpha equal to 0 is very famous because that is a K independent correction here, which describes a massive graviton. It's a massive particle. So what we see in this plot is this kind of, goodness of fit measurement, delta chi squared over the SNR rho squared is a way of saying how well or how bad these modified gravity waveforms fit my type 2 image that is lensed. And what I want to show here first is this alpha equal to 2 case that is really a proxy for unlensed general relativity, because alpha equal to 2 does not, it just rescales speed, the propagation speed, so it does not add any distortion. So it's the same waveform as an unlensed general relativity. And this, in what you see here, is for 2 different type of binary systems with different masses, arbitrary typical values that we choose to represent here. then how bad your unlensed general relativity waveform is going to fit this type 2 image that has been distorted. And well, you have this value of 0.15 or or a little bit lower, depending on the mass of the black hole. But the important thing is that for any other value of alpha, for example, for alpha equal to 0, which is massive gravity, or for other values of alpha, you can always fit better the signal. So modified gravity models fit better the lensed signal than unlensed general relativity. So this is why, I mean, at least we have been advocating for always checking for lensing as well from now on in the data analysis. However, this confusion here is not going to be a huge problem because this confusion is for a single gravitation wave that you detect. If there is truly a modification of gravity, we expect to have all of the signals modified, from general relativity, not a single one. So that is a piece of information that you can use to distinguish true lensing from modified gravity. So just to finish, I'm doing well in time. And just one scientific application, because I've been talking a lot about how we prepare and what kind of information we can use to claim confidently the first detection. But then what are we going to do with that? Well, we can do a lot of things, but just very broadly. So the typical time delays between the strong lens images, we already mentioned, is like a month, 2 months, 3 months or so, a few months. And what that means for gravitational waves is that the detectors that are on Earth will have rotated when the second image arrives, just because of the rotation of the Earth. So rotated with respect to the source, the major source. So that helps a lot because you have like a second basically detector, you duplicate all of the detectors, you detect the signal again, and they also have different orientations, which helps with triangulation. So, and it also helps with identifying and measuring the polarization of the gravitational waves when you have a lot of detectors with different orientations. So you can see exactly like in what directions space-time is oscillating. So that's the polarization. So these type of strong lens systems are very valuable to perform polarization tests because of what I said, but also to potentially get a much better sky localization of the binary source. So this is an example that other authors have done, but I find it very good to illustrate one of the applications, which is, what if we have a binary black hole that was lensed and we detected 4 images? So each one of these 4 images is going to have some kind of a sky location that here you see in the dashed lines that typically is going to be of like 10 degrees squared or so. So it's kind of a bad localization. But if you know that these 4 images come from the same source, you combine all of the information from them to get a much better sky location of 1 degree. So then what you could do is an electromagnetic follow-up. Then you could look for all of the galaxies that live in that 1 degree, square degree location in the sky and find for all the ones that are strongly lensed and try to find the galaxy that is the host. Why is that important? Well, first, because it helps with confirming that this is a strong lens event, because there has to be at least one galaxy that is the host that is strongly lensed. But it also helps because electromagnetic observations give us the redshift of the actual redshift of these sources, which is something that we usually don't get with gravitational waves. We don't know what the redshift is. And that helps, for example, with constraining H dot, that you always need an independent measurement of distance as well as redshift. So gravitational waves give you the distance, but this electromagnetic follow-up will give you the redshift. So for these type of images, with a single 4-image strong lens gravitational wave event, you should be able to constrain H dot with a precision that is, this is the estimation of like 9 kilometers per second per megaparsec, which is more than 10%, but this is a single event. So there are some claims. I mean, I think most of these forecasts sometimes are too idealistic, but there are claims that say that for measuring H naught with a strong lens gravitational wave events, you could achieve the same precision as with quasars, but with 10 times less events, for example. Because the time delays I already mentioned are measured very accurately, and you can do all of these electromagnetic follow-ups to find all of the redshifts. So this is one of the applications, but of course you can also use it to learn more about the dark matter distribution, that how it affects these different images of gravitational waves, which I think is also a very interesting way to follow up. So I'm gonna finish here, which is the summary. So the effect of lensing is unavoidable. We know what happened, and according to the planned detectors and the planned increasing sensitivities, it will be inevitable and maybe will happen already in 4 years. The strong lensed effect affects magnifications, arrival times, but also the actual phase of the signal through these constant phase shifts. And the lensing phase shift is very special. So all of these 4 images, for example, if we detect, they need to be shifted by discrete values that are these multiples of pi.5. So that is a piece of information that we want to use. Sometimes these phase shifts can be degenerate with some changes in the source, but I mentioned that sometimes it is not degenerate with changes in the source whenever we have inclined or unequal mergers happening. So they could be confused with modified gravity, but hopefully will not be such a big deal when looking at the overall population of events detected. So this phase shift has to be, I think, is a pretty important piece of information to identify strong lens events. And I already mentioned that there's a lot of more science that we want to prepare, mainly to learn about dark matter. So one of the main unknown properties of dark matter is how it behaves on a small astrophysical scales. And there's a lot of plans for using strong lens quasars for learning about small scale dark matter properties. And we can do the same for gravitational waves. And actually gravitational waves can suffer from additional distortions because of, in the phase, because of the small scale dark matter properties. So that's something very unique to gravitational waves that we want to exploit, but because of time, I didn't mention too much. So I'm just gonna finish here. Thank you.
Thank you, Macarena, for your great talk. I think we have some time for questions. So if anyone has one, please go ahead.
Thank you for the very talk. So you mentioned time delays of minutes for the additional waves. The case of let's see electromagnetic signals. People obtain that kind of short or...
So the typical time delays for quasars is a few months, like 2 to 3 months, most of the time, caused by galaxy. For gravitational waves, in principle, it's around like 1 month or within 1 month. It's a little bit shorter.
So being shorter means affecting smaller objects?
No, so this is just the actual time delay between the different images. So you can always detect all of the images, and the only question is whether, well, you need your detector to be continuously running for a year, for example. If you have 4 images, each one separated by 3 months, you need at least a year of continuous detection. If the time delays between the images are a little bit shorter, then I think that should be easier. Like you need your detector to be running for a shorter amount of time in order to actually be able to detect the 4 of them. So it doesn't really translate into your ability of like the type of sources that you're gonna be able to detect. And you mean for the mass of the lens?
Yeah.
So here we're actually assuming that it's galaxy lensing because that's the most common one that happens. Yes.
So candidates.
Yes.
Observe discrete phase or...
Yes. But I believe that they have the same phase. So 0 phase between them, which means that they're either 2 minimum. Well, yeah, they're to minimum, for example, and you never have only two minima images. So you need to have, you always create additional type 2 images. So there's like a parity type of argument that you always need to create a type 2 for each type 1 and so on. So that means that you should have missed a bunch of other images that need to be there. So there's actually a lot of arguments that one can use for these phase shifts at the end to additionally claim that these are not, very likely not to be strong lensed candidates. The chance that they are actually strong lensed, yes. So I think there may be like a few people in the world that still believe that there's some strong lens detections, but most people think that's not. We haven't seen it yet.
There's a question over there.
So when you show these images that you have this time difference, and then you shift one on top of the other to compare
Yes.
the same. So how do you shift? I mean, if I shift the curve on top of another, I can create any phase difference. What's
That's
the
correct.
calibration?
Yes, that's a great question. I always get the same question every time that I show this one. So the way we do it is by defining the frequency of the peak of the signal. So there's a varying frequency here as a function of time. So you calculate what is the arrival time of a specific frequency, you trace that, and that is what you set here as 0, the arrival time of that frequency. So this is what allows you, for example, here, because the evolution of the frequency as a function of time is what determines the amplitude, for example, as a function of time. So if you were to do shifting another way, you wouldn't be able to draw this envelope here as the same for both.
And is there a source of error there?
For the uncertainties. Yeah, I mean, it has to do with the uncertainties on like the phase that you measure, but normally that is like the best thing that we measure. What is the phase? Normally the amplitude has much larger errors and stuff like that. So, yeah, so all of these, here there are no errors, so this is just kind of a toy simulation. Theoretical.
Just out of curiosity, but a pie shift,
Yes.
they look the same or?
So a pi shift is a change of sign. So,
Right, okay, so.
Yes.
It would be the other way.
Any more questions?
So, many events. Bible have
mhm.
to finally get to the same decision. To measure it. They can. Or do we need to wait?
Yeah, like for the 1%.
Yeah, please.
Yeah. Are you talking about using this method of strong lensing or using another method? Because there's a bunch of different methods that we can use for gravitational waves to measure H0. So similarly, like for light, measuring H0 with a strong lensing is not the best one, mostly because of the systematic limitations of modeling the mass of the lens, the dark matter distribution in the lens. So there are better ways, which is the standard science approach, either because you have a binary neutral star that emitted light, so you know exactly the redshifts, or you do some statistical approach, like similarly to the sky location that I said here, like you have a black hole that has some kind of rough sky location, and you search for all of the galaxies, and you associate a probability that they may be the host, and also do some kind of a statistical redshift estimation. So most likely those will converge faster than this, especially because for LIGO Virgo detectors, when they're working at design sensitivity, we may only have 1 or 2 of these strong lens events. And there are planned upgrades that are not fully funded, so we don't know where they're gonna go through. If they don't go through, we have to wait for Einstein Telescope and Cosmic Explorer to be able to have these hundreds of strong lens events and get very good constraints on H0. But what I can tell you that I already mentioned just in words very quickly is that there are some estimations. I mean, sometimes they are, I think, maybe too optimistic, of measuring H naught with the strong length gravitational waves, that it converges 10 times faster than with quasars, just because of the time delays that are measured to millisecond precision as opposed to 1 day. And the time delay is the main quantity that we search for measuring H naught. But again, I think all of that's going to be limited by the dark matter uncertainties on the lens so far. So I'm actually personally more interested on ideally using these strong lens events for learning about dark matter, not for H naught.
So, any more questions? Okay, it's your honor. Let's thank again Macarena. And thank you everyone for coming today. Regarding the pizzas, we're going to have them outside, so you just have to follow me.